Drawing a rectangle on the screen was a big step, but it's not very interesting. The thing that separates games from other mediums is that it's interactive, so let's implement some input handling. We could just detect raw key presses, but we want to allow keybinds to be changed and saved. So for that we'll need some kind of configuration file. We know we'll need to write this file to disk, so now is a good time to fill out that write function we prototyped earlier. But before jumping into that, we'll quickly update our error macros and wrap them in braces. This will allow us to use them in more places without adding extra braces. Now inside io.c, we'll need to add a null check for our read function before moving on to the write function. The write function is pretty simple. First, we'll open the file for writing in binary format, just like we did with reading. Then we'll check for null or errors. Next, we'll call the fwrite function and just attempt to write the entire buffer in one chunk, instead of splitting it up like we did for reading. Closing the file, we'll then check to make sure we wrote the chunk, and then we'll return 0 for success. Inside engine, create an input.h file. Thus far, we've had the module headers inside their own folders, but I think it's actually neater to have the headers all in this engine directory, and then their various files inside their own subdirectories. I've gone ahead and moved render.h and io.h. In input.h, we'll define what keys we care about as an enum, and then we'll define another enum for the current state of a key. Next, we'll create a state struct similar to the other modules, and this is where we'll store the current state of each key that we care about. Finally, we'll define an update function that we're going to call each frame to update the input state. Creating and opening an input.c file will import some things we'll need: input, global, and types. First, we'll create a static function called update key state. If the current state is not 0, then we'll check to see if it was already pressed or held. And if it was, we'll set it to held. Otherwise, we'll set it to pressed. Then if the key is currently unpressed, we'll just set it to unpressed. Next, we'll create the update function. In here, we'll get the current key state from SDL. Then we'll update each key we care about. We haven't yet built the config module to store our keybinds, so we'll do that now. Create and open config.h, then we'll define a config state struct to hold our keybinds and 2 function prototypes, one to initialize the module and one to bind keys. Copy the function prototypes into config.c, and then we'll look at the init function first. If the config file doesn't load properly, then we're going to try to create a new one using this config default value that we have yet to define. Then we'll just call config load again. If it fails again, we'll exit the program. Let's define that config default value now at the top. In our case, we'll just bind WASD and escape for now. Now we'll create the load function. Make it static as it's not used outside this file. We'll just read the file. If that fails, we'll return 1. If it succeeds, we'll call another function called load controls, which we're going to make next. Then we'll free the data and return 0. Load controls, also static, we'll call config keybind and use the enum we created earlier, and a function we're about to create called config getValue. Before we create that function, we just need a static buffer here. 20 characters should be enough space. Config getValue is a very dumb parser for our config.ini file. First, we'll find the line that the value we want is on. If we can't find it, we'll exit the program and suggest deleting config.ini. Next, we'll find how many bytes until the end of the config file. This will come in handy in a second. The basic idea is we're going to find the value that comes after the equal sign, and then we're going to read that value into the temporary buffer, after which we'll terminate the string and return a pointer to the start of the temporary buffer. So we'll create 2 new pointers. Current is what we'll consider our current position in the config file, and then the next is temp pointer. We're going to use that as our current position inside the temporary buffer. First, we'll move the current pointer to the equal sign and past it to the next character. We'll use a while loop here to move past any spaces that are after the equal sign, and then once we hit any other type of character, we'll use another while loop. This one is going to stop when the current pointer hits the end of a line or a null terminator, or if we've reached the end of the file. Now inside this while loop, we're going to just copy the current value of current into the current position of the temporary pointer, and advance both pointers. Finally, we'll null terminate the temp pointer and return a pointer to the start of the buffer. The last function in this module for now is config keybind. It takes 2 arguments, a key enum and a string name. We'll get the scan code using an SDL function, then we'll set the keybind to that scan code, printing an error if the key couldn't be found. Make sure you don't forget to include config.h like I did. We're going to make one more module in this episode, and that will be for dealing with time. So create time.h in the engine directory. Like other modules, we'll have some kind of state. Let's go through each value here so there's a clearer idea of what these represent. Delta is the time between frames. Now is the time of the current frame. Last is the time of the last frame. Frame last is the last time the FPS was calculated. Frame delay is the maximum amount of time a frame should take. At the moment, we're naively assuming that our frames will always take less than this time. Frame time is how long the current frame took. Frame rate is how many frames per second we're running at, and the frame count helps us calculate the frame rate. We also need 3 functions: time init, time update, and time update late. As usual, copy the prototypes into time.c and we'll get cracking. Time init takes a desired frame rate, stores that on the global state variable, which we haven't made yet, and also calculates the frame delay using that frame rate. Time update is to be called at the beginning of each frame. We get and set the current time with SDL getTicks, then we update the delta using this new time and the last, divided by 1000 because we're storing the delta time in seconds. Incrementing the frame count helps us with calculating FPS, which is what the next block is for. Basically, we only run this next block once per second. Then we set the frame rate to however many frames we added up over that second and reset it to 0. Time update late is called at the end of each frame, and we'll make sure that we don't go above our desired frame rate. In the future, we'll be decoupling our game loop from the frame rate, but for now this will do. Next, let's update our global struct, adding the module states we just created. We'll also need to update our build script to include the new files we added. While we're here, we may as well remove the free type dependency as we're going to be using something else instead. It's finally time to update main.c and put all of this together. Include the new header files we created, config, input, and time. Now we're going to move that should_quit variable to outside the main function and make it static. You'll see why shortly. We'll also create another static variable, a vector2 called pos. This is just a temporary variable to test our input code. Now we'll create a static function called input_handle. Inside this function, we're just going to check if our movement keys are either pressed or held, and then update the position vector. We'll also add in a check for the escape key, which should set the should_quit variable to true. Down in main, we'll call time init with 60 as the argument for now. Follow that up with config_init. Then we'll initialize the position vector to the center of the screen. Inside of our loop, we'll call time update at the beginning and time update late at the end. After polling SDL events, we're going to call our input update function, and then the input handle function we just created. Finally, update the render quad to use our position vector. Then we can build and run the program, and you should see that you have a quad that can be moved around, and you can exit the program with escape.